I'll have to, and for that, I'll have to start a bit from afar. I'll start with talking about just tuples of natural numbers. So let's take any enumeration of tuples over natural numbers, just usual finite tuples of usual numbers. And then the functions that compute length and the function that computes length and the function that computes ith element of tuple number n, well, they're computable, so we can express them by some sort of first order formulas. Well, even actually just by equations, but whatever. So by first order formulas. So we are going to have formula T capital that says that tuple number n has number a in place number I. And we are going to have formula L capital that says that tuple number n has length k. And then we are going to ask what these formulas define over some arbitrary model of arithmetic. So for that, I need to talk a bit about that. So if you take arithmetic, well, in the usual signature, 0, 1, plus, and times, what does a non-standard model look like? And well, the partial answer here is that, well, first of all, once we have those operations, we can introduce order. So, well, we might have included it into the signature, but doesn't matter. We can express it through those operations. So we have order, and in terms of order, anything that's elementarily equivalent to n looks very simple because, well, first there is this, in the beginning, there is this chunk that's just isomorphic to n, and then above it, every element is going to come with the whole Z neighborhood because every element is going to have a predecessor and a successor, well, except for one, but one is not there. So every element is included with this whole Z neighborhood. And moreover, these Z neighborhoods they're kind of densely packed because if you take two different ones, you can always take half sum of two elements or almost half sum of two elements, like, you know, up to 1/2. So what we end up getting is, again, this chunk in the beginning that's isomorphic to n, and then you pick your favorite cardinality, take a dense order of that cardinality without endpoints, and put a z-stick at every point of that order, and that's altogether makes non-standard model of n in terms of order. Now, operations are way more complicated because, well, for one thing, both addition and multiplication, they are necessarily non-computable even in the countable case. Well, basically because there is like actually ultra filter like sitting like behind the screen there. But nevertheless, let's think what these formulas T and L that, again, ith coordinate and length of a tuple define over this n tilde. Well, whatever they do, we'll call those things non-standard tuples. And I'll justify this name a bit. So first of all, we can write down this formula right here. So this formula just says that every tuple has a unique length. So now we have something that's elementarily equivalent to n. So this formula is also true in n tilde. So now we know that every non-standard tuple has some unique length, but now notice that length is also non-standard. So length may be an element in n tilde that sits above natural numbers in the red part of the picture on the previous slide. And then the same happens with ith coordinate. We can write a formula that says that every tuple at every I of appropriate in the appropriate range has a unique number sitting there. So now our non-standard tuples, well, we don't quite know what they are, but we know that they have length and they have coordinates where at each coordinate there is some particular element of n tilde. So whenever we want to talk about these coordinates or length, we can just use those formulas and we can access them that way. What we can immediately notice is that whatever we get, we're not going to get all abstract tuples. So if you look at just, just set theoretically, just all possible functions from intervals in n tilde to n tilde, we're not going to get all those things, at least because of cardinality. Because say if n tilde is countable, then all abstract tuples are going to be not countable. And our object is in bijection with n tilde, so it will have to be countable. Well, yes, that's, well, yes, yeah. Right. So now, so even though this object is kind of mysterious, like for one thing, again, in n tilde, we do, like there is no actual way to compute operations, but nevertheless, we can look at well, what sort of things we can get here. For example, we can write a sentence: for every n, there is a tuple whose every component is 1. So now we have, well, tuple of length n whose every component is 1. So now we have this constant tuple of 1s. Similarly, we can write a sentence that for every n, there is a tuple whose ith component is I. So now we have tuple 1, 2, 3, and so on. And a bit more involved example. We can take a tuple of length n and again write a sentence that says that every component is between 1 and 10, and every number between 1 and 10 occurs exactly once. So now we have written that this tuple is a permutation of 1 through n. And again, not all abstract permutations are going to be there, but those of them who are non-standard tuples we'll call non-standard permutations. Right. So then, since this is a group theory seminar, so everybody probably thought, okay, do we get a non-standard permutation group? The answer is yes, we do, and I'll talk about it in a minute. But first, there is one more important thing that's actually going to be crucial for today. Just like we can define sum or product of a finite over a finite tuple, for example, sum of all elements in a tuple, we can do the same here. And when you look at it, there is this knee-jerk reaction that, well, this is actually an infinite object, so the summation will involve some sort of, limiting process of some kind. But no, there is no limits here, because we just do exactly the same thing that you would do in the finite case. That is, you define, if you want to say take a sum over a particular non-standard tuple, you define an auxiliary tuple that just starts with the same first element, and then you inductively say that each new element is just the previous one plus the respective ni in the tuple that we are trying to sum up. And then the last element of that auxiliary tuple is going to be the sum, well, and the same with the product. So now let's look at this more formally, because, well, what I did is basically called interpretation. So let me say a couple of words about that. So what we have here is, well, generally speaking, we have this arithmetic in the usual signature, and we can look at an arbitrary structure. And just to avoid worrying about it, let's say that L is finite. So just fine signature, just to avoid any sort of like weird questions. Then we can define least superstructure. So it's least superstructure over of A over N. So it's a three-sorted thing where one sort is the structure A itself, so together with its signature and everything. Another sort is N, and one more sort is, well, denoted by the word list. It's just the set of all lists, or I've been calling them tuples so far, just a set of all finite lists of elements in the underlying set of the structure A. And then on top of that, we add two more predicates, exactly the ones, again, that you expect. The one predicate says that, again, tuple S has element A in place number I, and another, well, you can think of it as a function or predicate, it gives length. So this whole setup that we did is we took least superstructure S and N, and we expressed everything that's going on there through formulas over N. So this is called an interpretation. So what we did is interpretation of S and N in arithmetic. So this collection of formulas. So again, basically, what does this collection of formulas include? It's a way to represent elements of the structure that you are interpreting. And then for every predicate and operation, some formulas that allow to define them. Again, over the structure in the right-hand side. So we had this collection of formulas, and then we considered all the same formulas. So in our case, it was just L and T. We considered the same formulas over something that's elementarily equivalent to N in our case. And what we got is an object elementarily equivalent to the least superstructure. So more precisely, this actually, you can do it not just with least superstructure of N and N, you can do it with, in more or less arbitrary case. That is, if you have a structure B that's interpreted in a structure C, well, modulo some technical details, then if you take the same interpretation over some C prime that's elementarily equivalent to C, the result is elementarily equivalent to B. So this is what we did. We had interpretation over N, then replaced N with N tilde. And moreover, this actually is well defined in the sense that if you have two different interpretations and you plug in the same structure in them, the result does not depend on the choice of interpretation. So our object, the non-standard tuples, is actually well defined. So now I want to give a couple examples how we can deal with this, with the object that we obtain this way. So first example is to emphasize that, well, basically everything that we can express by first order theory carries through, of course, because literally that's the point. For example, with finite tuples, there is this very easy statement by counting that if you have a tuple of length n, and you know that every number from 1 to n actually appears on that list, then it appears exactly once, and nothing else has any room left to appear. So if every element between 1 and n actually appears in a tuple of length n, then the tuple is a permutation. So now we can state the same thing about non-standard permutations. So if you have a non-standard tuple of length n, where every non-standard natural number between 1 and 10 actually appears, then the tuple must be permutation just because of elementary equivalence. A slightly more involved example, and is going to be about this permutation group Sn. And I'm not giving it because I'm particularly interested in specifically permutation group right now, but because I hope that it transparently illustrates the idea that I'm going to use today several times. So in the usual finite group Sn, there is this well-known statement that every permutation is a product of adjacent transpositions. For example, here I wrote an expression of arbitrary transposition as a product of adjacent ones. So let's ask, is the same statement true in the case of non-standard permutation group? And there is an issue, and I'm taking it in quotation marks because that's actually not much of an issue, but at least superficially, there is this issue that if you want to take advantage of elementary equivalence, well, we cannot because Sns are finite, so there is no non-trivial elementary equivalence there. But we don't care that much because we can think of this not as a statement about Sn, but rather a statement about the least superstructure. And in the least superstructure, we can easily write down that, well, the following statement. So let me explain here. So it says that if phi capital, well, if S is a permutation on n elements, so if S is a permutation on n elements, then there is a tuple of numbers Ti such that the product of these adjacent transpositions defined by Ti's is equal to S. And we can write all of that in the language of least superstructure, well, by approaching this product the same way as I explained this summation a few slides ago. So now this formula, it takes place in the finite case. Well, therefore, it's going to take place in the elementarily equivalent non-standard least superstructure. And therefore, when you look at what this formula says in the non-standard case, well, it says that every non-standard permutation is a non-standard product of adjacent transpositions. So that's kind of basically one of 2.5 ideas that I'm going to use today. That sometimes instead of looking at the object itself, we look at in this enveloping least superstructure, and there we can actually write down a lot of sentences, and they then transfer to the non-standard case. Okay, so. All right, so I went over the stuff. Yeah, so there is now a small detail here. Let me see. 20 minutes. Okay, I'll skip that detail. So if there is time, then I'll speak about it. So, so now there is even better news. This gets even stronger than I've been telling so far, because under some mild, well, mild, not mild, kind of arguable, but under, let's say, reasonable additional assumption, and I'll explain what the assumption is. This way of producing elementary equivalent structures to a given structure B actually produces all of them, not just some. So again, so this, as I said, a lot of this stuff appeared in those 3 papers by Alexey, Olga, and Mahmoud. So this is one of the statements that is kind of implicitly present there. It was just wasn't stated there out loud, so to say. So now let me explain what's going on with this theorem. What is this actual requirement to make all structures elementary equivalent to be describable as interpretation applied to some structure elementarily equivalent to C. So the condition is like this. So B has to be interpreted in C, and there has to be a reverse interpretation. So C has to be interpreted in B. So we can draw this picture. There is a copy of B inside C that's by interpretation gamma. And then by interpretation delta, we can take all this and put it inside B. And the condition that we need is that this little twice interpreted copy of B, it has to be definably isomorphic to B capital. So now if we had this in both directions, so if we had also a copy of C sitting definably here, then this whole thing would be called by interpretation. So here we only require half of that. And yeah, so for those who know the terminology anyway, I'll say that here we do not require that this isomorphism is precisely the composition of coordinate functions. It can be any isomorphism. As long as it's definable, we are happy. Okay, so now I'm finally done with this preliminary stuff, and I can get to talking about polynomials. So let's see how we can use it to figure out elementary equivalence in the case of a ring of polynomials. And so before I say anything, I'll point out that so we can deal with polynomials over Z or over a field. It doesn't make that much difference. And actually, the case of polynomials over Z is a bit harder, just because Z is a bit harder to dig up inside the ring of polynomials using first-order theory. But I think that as a black box, this polynomials over Z should be kind of probably easier to grasp. So I'll just start with this case, and then I'll And then I'll talk about the case of a field. So the statement is that this ring of polynomials, it has that kind of interpretation that we need in the least superstructure of Z. Well, and therefore also in N, because least superstructure of Z, well, it's very easy to interpret in N. Well, there is not much difference between superstructure of Z and N in the first place. So now we get this immediate corollary that every ring that's elementarily equivalent to the ring of polynomials over Z has this form. So gamma is our interpretation, and we just take this gamma, pick our favorite non-standard arithmetic, plug it in there, and that's going to be the ring. Nice, but by itself it doesn't get us anything. We just said that, well, this strange object is actually that other strange object. So let's actually look how this gamma works in more detail. So once we look at how gamma works, we'll actually have a very clear idea like what those gamma of n tilde are. So running a bit ahead of ourselves, we'll call them elements of this structure. We'll call non-standard polynomials, and well, we'll justify the name in a few minutes. But let's look at the interpretation. So interpretation is basically as straightforward as it can be. So if you want to interpret polynomial with coefficients a0, a1, and so on, well, that's the tuple. You just write down the tuple of coefficients, and that's the tuple that interprets that polynomial. So there is this technical detail that again, behind the scenes, we need the reverse interpretation, and the reverse interpretation is actually more complicated. But again, just to understand how the object functions, kind of at the level of general idea, I'm not going to go into those details. So now what happens when we replace n with some non-standard model n tilde? Well, our tuple just becomes non-standard. That is, it's now indexed by these non-standard natural numbers, and its elements come from Z tilde. And so Z tilde is just n tilde minus n tilde, so there is no mystery there. So Z tilde just looks like a dense order, and then, well, basically, like if you go, okay, so yeah, I understand. So now imagine that basically there is a symmetric picture on the left here. So this blue stick, it might as well be one of the red sticks, because it's just now every point just has a Z neighborhood. Well, yeah. Right, okay. So then if we do some almost tautological juggling of formulas, what we can get is that every element of our mystery set, we can write it in this form. We can write it in this form where, well, so kind of to explain what those tautological formulas are. Well, we can take a tuple of coefficients that looks like 0, 0, 0, 0, and then 1, 1, and then a bunch of zeros. So that's x to power I. Then you take those tuples, you can then sum them up with coefficients ai. And again, summation is in the sense that I explained before. So if you understand this formula in that sense, then what you get is that this non-standard sum corresponds to the tuple a0, a1, and so on. So now we basically explained that the elements of our mystery set, they just look like usual polynomials, only instead of finite summation, it's non-standard summation. And then operations are also can be easily defined in terms of these summations. Well, exactly by the same formulas that you're used to, just we again view them as non-standard summation instead of finite summation. So now let's look for a minute what sort of algebraic properties we get there. So first of all, we thought for quite a while how to denote this object. We didn't come up with anything good. So the best we came up with is notation like that. So if you, all right, so So the idea is that it's something like a tensor product. So if you say want to complexify, say, I don't know, a vector space, you take tensor product with C. So here we have polynomials over Z, and we want to make them over Z tilde instead. So we kind of take this, kind of like tensor product within tilde to make all coefficients non-standard. But it's of course not fair to call it tensor product. It's not even close. But well, that's kind of the least bad notation that we came up with. Well, because basically every proper notation would have to involve the original object, then the interpretation, and this new set over which you're interpreting. So it's like whatever you come up with is going to be cumbersome. But anyway, so first of all, there are some properties that just carry over because of elementary equivalence. For example, if you have two polynomials, and let's just say I'll talk about just single variable, and as I have been, just not because there is much difference, but rather because just less writing. So let's say single variable polynomials, you have two coprime polynomials, then there is this Bezout theorem that says that there are, you can express their GCD, in this case one, as a linear combination. So that's a statement of first order theory, so it just carries over immediately. There is more interesting stuff though. So first, let's notice that this ring of non-standard polynomials, it's not a unique factorization domain. And the problem is actually not with the uniqueness part, it's with factorization part. If you take x to the n with non-standard n, then you cannot express it as a finite product of irreducible polynomials. Well, you would like need infinitely many. But this example just doesn't really tell us that it's not UFD. It's actually telling us that we shouldn't be looking at the finite factorizations in the first place. What we should, ideal as a principle, yes. Yeah. So this unique factorization thing, it does work. You just have to consider non-standard products. Namely, if there is a non-standard polynomial Q, then there is going to be a non-standard tuple of irreducible polynomials such that Q is equal to the product of that tuple. And moreover, this factorization is unique up to, well, precisely that kind of non-standard permutations that I explained in the beginning. So up to non-standard permutations and up to invertible factors, this representation is unique. And well, here you can actually think about this in two ways. So on the one hand, you can just look at the proof and you can recover it step by step, and like it works basically because of Euclid's lemma. But also, well, yeah. But also you can write all the same stuff in the language of the least superstructure, and it's going to be satisfied in the case of standard arithmetic, and therefore in the case of non-standard as well. A similar thing happens to Noetheriity. So again, this ring is very much not Noetherian, because if you start with a non-standard power, you can descend infinitely. So your ideals keep increasing. But that's just because, again, we're not looking at the right thing. We should not be thinking about finite chains. We should be thinking about non-standard chains. And then you can formulate that, yes, it is non-standardly Noetherian. Okay, so now one last thing. So like there are several properties like that, so I don't want to go through all of them. So one last thing that I want to talk about, I want to say something about is the universal property. So the idea is that we want a statement of the kind that says, if you have some ring or some algebra over Z, for example, well, same thing, but whatever. So, and you take any mapping from X to a particular element of that algebra, this mapping can be extended to a homomorphism. So you want to say something like that. And the first question is, what is that class of algebras that we want to be looking at? Well, because for one thing, if you want to, if you want it to have something to do with this non-standard polynomials, we do need to have the same kind of non-standard summation there, non-standard multiplication, so all that stuff. So maybe there is a way to somehow axiomatically define all that, but for the moment, let's just be cheap and say that let's take a ring that's interpreted in N. Let's take, well, by the way, not a big restriction. So it's if you have arithmetic word problem in your ring, it's going to be interpretable. But anyway, so let's take A tilde, which is just, again, the non-standard model of A. And let's ask, is it true that every mapping from X to some A extends to a homomorphism? And we run into this immediate issue, because if you remember how this kind of very straightforward thing works in the finite case, it's basically by saying that, well, I have a homomorphism, and therefore I can take any element like that and push phi inside, and then I know what my phi of this sum is. But for this, we need to have, so to say, non-standard homomorphisms. We need phi to respect not just finite sums. We need it to respect non-standard sums. This is, at least superficially, that's a difficulty, because that's not a property of, say, first-order theory of polynomials or of A or anyone's first-order theory, really, because again, you have this mapping from polynomials to another ring. But we can use the same idea that I introduced before to circumvent this. That is, you place everything inside the least superstructure. And now the statement that you have a homomorphism can be written in that superstructure. And then you can write a formula that says, if phi respects sum of two elements, then it respects a sum over a tuple. And then over a and over N tilde, that becomes a statement that if phi respects sum of two elements, then it becomes then it respects sum over a non-standard tuple. So what we can figure out here, in other words, is that in this setting, every homomorphism is automatically a non-standard homomorphism. And then, like, the usual proof just goes through immediately. Okay, so before moving on, let me briefly talk about the case of polynomials over a field. So let me actually check the time. Oh, do I have 50 minutes or 60? Okay, 60 or 70? Okay, so all right. So the thing is that if you want to have polynomials over a field, in the context of what we already talked about, the easiest thing is to just restrict ourselves to fields that are interpretable in N. Well, because then, like, ultimately you just have interpretation in natural numbers again. So you can interpret then, if your field where the coefficients live is interpretable in N, then you first interpret polynomials in the least superstructure of that field, and then you interpret the field in natural numbers. And that, like, if you compose, it leads to interpretation of polynomials in natural numbers, and then you do all the same stuff that we did before. Actually, we don't need to assume this. So if you don't assume that your field is interpretable in N, nothing really bad happens. It's just you have to, your interpretation will just stop at the least superstructure, and instead of taking N tilde, you would be taking some object that is elementary equivalent to that least superstructure. So not much really changes. So that's my point. But just to keep, again, things kind of as grounded as possible, I'll stick to this case, at least for the moment, to the case of field interpretable in N. So then all the same stuff still works, so even easier than the case of Z, like I said. So F can be, this ring of polynomials can be interpreted in the right way in natural numbers. Therefore, we again conclude that every ring elementarily equivalent to this ring of polynomials has the form gamma of n tilde, and the elements of this gamma of n tilde are the non-standard polynomials, and they work pretty much the same way that I explained about Z. The only difference is that now the coefficients are not from Z tilde, they are from F tilde, where F tilde is the like whatever you get when you replace n with n tilde in this interpretation. Let me see. Yeah. So here I want to mention that, of course, there are these classic results by Baval that, well, for example, they describe all Noetherian rings that are elementarily equivalent to polynomials, which is a good thing because remember that our stuff is not Noetherian. So if it was Noetherian, then we would have a problem. But the rings that we build, they're not Noetherian, so these theorems, at least they don't contradict to what I've been saying so far. Okay, so then you can do very similar thing to Laurent polynomials, both over Z and over a field. And you can also look at the group algebra of a free group, about which Alexei and Olga know that it's bi-interpretable with the least superstructure. And therefore, all the same stuff also works there. I'm going to skip over all that stuff because to look at it in detail, well, we first need to understand about this interpretation of free group in N. So instead of talking about this free group free group algebra, I'll just talk about the free group itself, and then once we get through that, how it will be very clear how this interpretation works. So now I'm about to switch to talking about the free group. Before that, just one last thing that I want to say out loud. So again, so this is something that I already mentioned a couple minutes ago. So again, what happens if you want to pick a different, what if you want to pick a field, say like R or C or something that's not interpretable in natural numbers? Well, so everything still works. It's just our kind of interpretations, they stop at the least superstructure of the field, and we don't descend further to interpret an N, we just stop there. And then these non-standard models, they are produced by a choice of structure that's elementarily equivalent to this superstructure. And those things are a bit not entirely clear how they work, but what is clear is we can treat those elements, the elements of M, just like we do tuples, because we have elementary equivalence. So every element of M is going to have some length. Every element is going to have something in its ith place. If two different elements have all the same coordinates, then they're equal. So like we can treat them as tuples. We can still treat them as tuples, even though like there are some questions that are not clear how to answer there, but still. So then basically all our theorems still hold up with the change that instead of taking n tilde, we take something that's elementarily equivalent to this superstructure. Okay. So now let's get to free groups. And with free groups, there is an immediate problem. If you want to interpret a free group in N, and then take this interpretation over something that's elementarily equivalent to N and see what happens, our theorem 2 in the beginning that said that the object that we get does not depend on the choice of interpretation, it doesn't apply anymore because there is no reverse interpretation. So there is no invertible interpretation of a free group in natural numbers. but nevertheless, we still have the well-definedness, well, because basically over n, you can kind of just enumerate everything. So that's why if you have something that's interpreted, just interpreted, so not necessarily invertibly interpreted in n and 2 ways, then the result that you get when you use n tilde instead of n, it's the same for both gamma 1 and gamma 2, again, just because you can basically enumerate all your elements. So now, if you take some interpretation of free group in natural numbers, which I'll describe in a moment, then we can produce a family of structures that are elementarily equivalent to F. So now let's pick one interpretation and see what we get out of it. And again, let's be kind of as cynical as possible here. So if you have a group word on generators, xi1 to power plus minus 1 times x2 to power plus minus 1, and so on, how we can record this over n? Well, I'll just record it as a tuple where I'll just put i1 for xi1, then I'll follow it by i2 for xi2, and so on. And then I'll also slap a minus every time I want to have inverse instead of the element itself. For example, if you have a group word that starts with x2, x1 to power minus 3, then interpretation is 2, minus 1, minus 1, minus 1, and then whatever else. So 2 for x2, then minus 1 for x1 inverse, minus 1 for x1 inverse, and so on. So that's the interpretation of elements. Now we need to interpret the operations. So to do group multiplication, like in the terms of these tuples, of course, what you do is you just concatenate, and then you just excise the biggest tuple that kind of cancels out. So this way we get interpretation of free group in this least superstructure of Z, and therefore we can ultimately get interpretation in N. And that way, when we take this interpretation gamma that we get as a result of all that, and we use any other n tilde with the same formulas, we get some sort of group, and we'll call it non-standard free group. Now, an immediate note here is that this F tilde that we get this way is elementarily equivalent to F, but of course there are plenty of groups that are not like that. For example, like surface groups. What it means is that this interpretation actually is not invertible. So, well, it was clear before anyway, but now extra sanity check. So let's look in a bit more detail how this interpretation works. Well, for example, so in the finite case, there is this, again, easy statement that if you have two words and they give the same element of the free group, then there is a chain of free cancellations or insertions that will take you from one element to the other. So is the same thing true in the non-standard case? And here again, we run into the superficial problem is that in this first order language of F, we don't have access to those tuples because there is no invertible, there is no reverse interpretation, so there is no a copy of N sitting inside of F that we can access. But of course, that's not much of a problem because again, I'll use the same trick as before. I'll say that instead of language of F, I'll just look at the whole list superstructure. And then in the language of that list superstructure, it's very easy to write down the statement that there is a tuple of words where you start with W1 and you end with W2, and every adjacent pair differs by a single cancellation or insertion. And then the same statement is going to be true for the non-standard tuples. Well, therefore, now we get the statement that if you have two words in the non-standard free group, and they record the same element, then there must be a non-standard sequence of precancellations and insertions that will take you from one word to another. Yes, yes, except the formula is not over F, it's in the list superstructure. Or again, so just like with usual free group, instead of thinking about freely reduced words and concatenation with like this one big cancellation, you can take any word and again record it by the same sort of tuple as before, only now I am looking at not at the tuples themselves, but rather at equivalence classes. Well, again, under this usual free cancellation or insertion. And this also gives me an interpretation of a free group. And the point is that since our object is well defined, this way I get exactly the same group as before. So the moral here is that with this non-standard free group, well, you like at the level of elements, you can do all the same stuff that you're used to doing with usual free group. Only whenever you have a tuple of something, you just replace it with non-standard tuple. But otherwise, it's all very familiar. Okay, so now there is, well, basically, I have like 1.5 points to make here. So first, I'll make this half point, and I'm saying half because, again, it's the same idea that I've been repeating several times already. So, for example, let's take this statement that in the usual free groups, like usual finally generated free group, every finitely generated subgroup is free. And we want to again see if this something like that is true for the non-standard free group. And the trick is again that if you just look at the first order language of the free group itself, well, you cannot write any of that down. But instead, we'll just look in the list superstructure, and in the list superstructure, it is very straightforward to write that one element lies in the subgroup generated by this list of other elements. And then it is also not that hard to write down that elements y1, say, through ym, they freely generate their subgroup. And then you can put that all together, and what you get is the statement that for every m elements in the free group, there are yeah, I shouldn't have written m here. So this was supposed to be less than m, but whatever. So there is oh, right, okay. So no, fine. So technically I do want this m here, but then I say that one of the following is true. So first new elements of those y's generate a free subgroup, well, freely generate a subgroup, and membership in the subgroup generated by y's is equivalent to membership generated by in the subgroup generated by a's. And again, so this is a formula not in F, it's a formula of the list superstructure. And then the same formula, yeah, and then so the small detail here is that we could also have been using, instead of actual formula with like m separate variables, we could have been using a tuple here and a tuple here. But anyway, so what do these formulas say over the non-standard superstructure? Well, first of all, products now become non-standard. The freeness is now about not just finite words being non-trivial, but also non-standard words being non-trivial. And this last big formula, it records this theorem that says that if you have any non-standard tuple of elements of f tilde, then there is at most as long a tuple of free generators that will generate the same subgroup. Yeah, so if you just use separate variables a1 through am, then you get the statement that every finitely generated subgroup is non-standardly generated by at most m elements. And if you use tuples, you get the statement that every non-standardly generated subgroup is freely non-standardly generated by at most that many elements. Yes, yes. Yeah. So, and then like similar stuff works for pretty much everything. So there is a non-standard version of Stallings Followings, there is non-standard length function, Nielsen generators, like pretty much everything like classically proved about free groups. If you replace the word finite with the word non-standard, it goes through. Okay, so then, so there is 5 minutes left, but have to choose here. So I can either talk about exponential groups or about ultra-filter thing. So I'll skip over the exponential groups because so the short version is that this, if you have been to these 2 talks by Alexei, then there is this notion of an exponential group where you basically take your group and try to figure out what happens if you allow exponents not just from Z, but rather from arbitrary ring. So our group F tilde, it allows us to use exponents from Z tilde. So it's literally a Z tilde exponential group in the same sense that Alexei talked about. And there are some questions there. Just for lack of time, I'll skip all that. And I really want to say something about this ultra-filter thing. So this is I said that there are like 2.5 ideas in this talk. So that's the second. So let's do the following. Let's take some decent ultra-filter on N, and let's take the ultra power of the usual honest hardworking free group, and with the same ultra-filter, we'll take an ultra power of N. So first of all, this ultra power that I denoted N star, so far I've been denoting them by N tilde, so I'll just keep doing that. So since this object that I got here is elementarily equivalent to N, I'll just denote it by N tilde. So now I'll look at 2 things. I'll look at this ultra power F star, and I will also look at the non-standard free group F tilde that I get by using this N tilde as my base. So these are hypothetically 2 different groups. However, notice that F star is going to be saturated, because so for that we need continuum hypothesis, but let's not worry about that. So let's assume continuum hypothesis, then F star is saturated, but so is F tilde, because it's interpreted in the saturated thing, therefore this is going you can see that it's going to be saturated. So what it means is that under continuum hypothesis, what we did is we just explicitly described ultra power. So it's it's a long-standing question by Maltsev to describe what ultra powers of F look like. So this is that. Well, of course, this is a bit of cheating, because what we really did is we offloaded all the difficulty into N tilde, but the point is that once we kind of accepted that we work with N tilde, then modulo that, the structure of ultra power, which is this incredible, complicated object that's even impossible to basically imagine, the structure suddenly becomes very clear. It's just this non-standard tuples over n tilde with some couple extra rules thrown on that. So this is as ridiculous as it sounds. It's an explicit description of ultra powers. And then, so I'm not going to have time to expand on this, but if you look at this bit of reasoning, of course, it's not particularly important that we had free group. You can do the same sort of trick with, well, pretty much anything as long as it has arithmetic word problem. And then what you get is you can take any finitely presented group, look at its ultra powers, and suddenly you understand them as well as, again, these non-standard models of G under just straightforward interpretation G in natural numbers. Well, and then like there are questions that pop up there, but and then like there is this whole kind of theory of non-standardly presented groups that kind of naturally arises here. But since I'm very much out of time, I'll stop here and I'll leave it to your imagination. So the answer is depends on what you exactly mean. So, so there is a way. So there is a way to understand this question that has answer yes. Yes. So yeah, so there is this kind of universal property of non-standard free group. Basically, if you have this G tilde that you obtain that way, then there is a homomorphism, and its kernel is going to be this. You just have to carefully explain what this is. Right, like independent of like actual like model theory stuff would be nice, not sure. But what we so the problem is that like so it's a good idea to try kind of to axiomatically describe what do you want from this object. So if you want to somehow define these non-standard groups in general, like what do you want from them, somehow axiomatically define. The problem there is that whatever you do, you're going to have those non-standard products, and you have to somehow explain how to do this multiplication and like pretty much everything about this non-standard products, or generally like do stuff with non-standard tuples. And that, at least looking at it naively, leads just back to this notion of superstructure and just taking something that's elementary equivalent to superstructure. So maybe there is a way to do something more intelligent. We're not sure yet.